Okay, let's look at this 2014 question. Okay, this one here is question 3, and you can see that here we have a standard cell. So let's talk about this. We have 2 electrodes. We got a tin electrode over here. We got a copper electrode over here. And the copper is in a 1 molar solution that has copper. The fact that it has nitrate, we don't care. And this is in a 1 molar, this tin is in a 1 molar tin solution. Then again, the fact that it's nitrate, that's spectator ion, we don't care. We have to figure out which one of these is the anode, which is the cathode. What are the reactions that are going to occur? Sometimes we would be given equations that would tell us, which one is more likely to gain electrons, the reduction potentials, but we don't have that here. So let's read. A student is given a standard galvanic cell represented above that has a copper electrode and a tin electrode. As current flows through the cell, the student determines that the copper electrode increases in mass and the tin electrode decreases in mass. So that is the big clue. So if copper is increasing in mass, then that means that the copper ions must be picking up electrons and turning into copper metal. Okay, that means that the ions that are in here are going to be picking up electrons, and they're going to add on to this, so this guy's going to get bigger and bigger and bigger as we go along. Okay, gaining electrons is reduction. We talked about Leo the lion says grr. So this is grr over here, so that's reduction. And that means that this side over here, this must be the cathode. So all that we can get just from the fact they said that that copper electrode is gaining mass. Well, if this is reduction, over here there better be oxidation. And that means on this side that the tin metal must be losing electrons. Okay, so it's turning into tin ions and giving up a couple of electrons. So this guy over here, we're going to call this side the anode. Now, because in the solution, we said the metal is losing, then this guy is actually going to end up getting smaller as the reaction occurs. And that's what it says. So this guy is going to lose electrons, and if it loses electrons, those electrons are going to pass through this outside circuit. And so the electrons are going to get over here to this side. So identify the electrode at which oxidation is occurring. Explain your reasoning based on the student's observations. Okay, oxidation occurs at the anode. Okay, so we're going to say it's the tin side. That's where the oxidation occurs. And why? Because if the tin is losing mass, then that means that the tin metal must be turning into ions. So the tin metal, okay, is turning into ions, and that's why it's losing mass. Okay, that's losing electrons, which is oxidation. So we will put that into kind of nicer terms, but that's the idea. Now, as the mass of the tin electrode decreases, where does the mass go? Well, a really common answer here for students was they were saying, that this guy here is losing mass and it's losing electrons. So the reason it's losing mass is because it's losing electrons, and that just is not true. Tiny, tiny, tiny bit of mass really. But what's going on is that this is losing mass because the metal is turning into ions. So all that mass is the tin metal going into solution. So the mass is going into the solution. So as the tin electrode decreases, where does the mass go? Okay, the mass is the tin metal turning into ions. And that's where all the mass goes. So we're talking about that little piece of metal right here, okay, is going to lose mass as it breaks up into ions. Okay, in the expanded view of the center portion of the salt bridge shown in the diagram below, draw and label the particle view of what occurs in the salt bridge as the cell begins to operate. omit solvent molecules and use arrows to show the movement of particles. So first off, I was confused by this when I first read it, and what I finally realized is we're talking about right here, we're looking at a close-up of that little piece of the salt bridge. So here's the salt bridge, and what's going on in that tube is that there are K+ ions and there are NO3- ions in that salt bridge. Now there's a couple ways that you could do this, and one is you always remember that anions go to the anode and cations go to the cathode. So you say, okay, anions and cations. Okay, cations are positive. Okay, cations are positive. Like little cats, little T in the cat just means cations are positive. So this guy here, this top one here, this one is the K+ is the cation, and this is the anion. And if we remember over here, here's our anode. So the anions go toward the anode, and the cations go toward the cathode. So I would say my anions are going to go this direction, and my cations are going to go this direction. And that's really all they were asking for. Now, why does that happen? That's actually a more important idea. So if we go back and look, on this side, over here, we have positive ions forming. Okay, we have neutrals turning into positives. So because we're getting more and more positives on this side, the solution has to stay electrically neutral. So negative ions are going to flow this direction in order to keep this solution electrically neutral. In the same way, over here, our positive ions are getting turned into neutrals, so we don't have enough positive ions, so the positive ions are going to go, to the left and come back into this guy, and again, to keep it electrically neutral. So the positive and negative ions are going to flow whichever way it has to in order to keep the solutions neutral, but the way to remember it is anions go to the anode and cations go toward the cathode. Now, a non-standard cell is made by replacing 1 molar solutions of copper and tin, that's what makes it a standard, with 0.5 molar copper and 0.5 molar tin. The volumes of the solutions are identical to those in the standard cell. Okay, so is the cell potential, and we're talking about the voltage, is the voltage of the non-standard cell greater than, less than, or equal to the cell potential of the standard cell? Justify your answer. Now for this kind of a thing, okay, we really kind of need to look at the overall reaction. So what do we have happening? We got copper ions, and they're going with tin metal. So if we put the two equations together, okay, we're going to say we have copper ions, and we're mixing it with tin metal. And what's happening is that the copper is going to turn into copper metal, and the tin is turning into tin ions. And if we did this separately, we could say, okay, there were 2 electrons being gained, 2 electrons being lost, so this is our balanced equation right now. Now, if we want to talk about, well, what's going to happen to the voltage, we want to say, well, what's going to happen to Q? Now, if you remember what Q is the same thing as KEQ. Okay, it's the concentration of the products and the reactants, okay, over each other. Don't put in the solids. So it's the concentration of tin ions over the concentration of copper ions. And what happens is if we put in, 1 molar here for a standard cell, 1 molar here for a standard cell, okay, we can see that Q is going to be equal to 1. But if we put in 0.5 for tin and 0.5 for copper, then Q is still 1. Okay, so, which way is an equation going to shift? Well, Q versus K, but since Q is not even changing, then there's going to be no shifting. Okay, it's not going to react, it's not going to drive the reaction forward, it's not going to drive the reaction in reverse. Now, what is a bad thing to tell kids to say, okay, and this is something that I have to stop myself from doing, and that is, don't do Le Chatelier's principle. Don't say, okay, that since these are the same, it's not going to shift to the right or shift to the left. This is not a system at equilibrium. An equilibrium battery is a dead battery, and this is not a dead battery. So this is not an equilibrium, so don't talk about shifting to the right or shifting to the left. Sometimes if you think about it that way, like a multiple choice question, it'll give you the right answer, but that's not the right reason. So the right thing to do is to look at Q, and if Q is the concentrations of the products over the reactants, and since Q is going to be 1 in both cases, then we're going to get the same voltage in both cases. Now the last little part here says both the standard and non-standard cells can be used to power an electronic device. So this is the battery. We can use it to do something. Would the non-standard cell power the device for the same So would the non-standard cell power the device for the same time, longer time, or shorter time as compared with the standard cell, and justify your answer? So we're saying we had 1 molar this and 1 molar this. Now we're going to put 0.5 molar and 0.5 molar. Well, what's going to happen is this chemical is going to run out more quickly. So it's going to be a shorter time. The copper will run out quicker. Okay, because it's just less chemicals, so the reaction is just not going to last as long. So we still get the same voltage, but the cell is not going to run as long. Now we go back here. In another experiment, the student places a new tin electrode into a solution of copper nitrate. So now we're just going to do a different kind of a reaction. So here we'll have a beaker. And in that beaker, we're going to have copper ions, and we're going to have nitrate ions. We don't really care about those. Those are spectator ions. And into that, we're going to place a piece of tin, metal. And so, using the information from the table above, write a net ionic equation for the reaction between the tin electrode and the copper solution that would be thermodynamically favorable. Okay, what's spontaneous? And justify the reaction is thermodynamically favorable. Okay, let's look at our numbers here. And what do we have? We have copper 2+, so we want this reaction is involved. And we have tin metal, and we know from above that tin metal turns into tin 2+. So we're going to have this equation involved. So what's going to happen is if we have copper metal, copper ions, okay, turn into copper metal, that is actually, going to happen better because it's got a larger E0 value than tin ions turning into, okay. If this reaction is going to go forward, that means this reaction down here is going to have to go in reverse. Okay, so the idea is what's going to happen is copper and tin metal are going to react and turn into tin ions and copper metal. So let's write that equation. So we're going to say copper ions plus tin metal turns into tin ions and copper metal. Okay, and if I do that, I'm going to combine these two. So there's a couple of ways to look at this. One is the voltage that we're going to get. Okay, the E0 value is going to be the difference in these two numbers. So it's going to be positive 0.34 volts, subtract minus negative 0.14 volts. That's really sloppy, sorry. So that's going to end up being, add those up, positive 0.548 volts. Now because we get a positive voltage there, that means it is going to be thermodynamically favorable. So just saying that that gets a positive voltage is enough to say that that is thermodynamically favorable. Now you could also go back and say, well, this is what happened. We told it in the cell above, that the copper actually, turned into copper metal, gained mass, and the tin, lost mass, and that's consistent with that information above. So you could do it with or without the numbers. Okay, finally, calculate delta G for this reaction. Well, if you look on the table, the stuff of different kinds of calculations, there are three big related ideas in chemistry, and that's the delta G, the KEQ, and the voltage. All three of those, will tell you whether a reaction is product favored or reactant favored. And a positive voltage, means that this reaction is going to go. Okay, a delta G that's negative, okay, that means that it goes. And the other one, that a KEQ that is greater than 1, that also says that a reaction goes. So those three ideas are kind of interchangeable. There are equations that will let you go from one to the other. So we just have to find the right equation, and it's the one that says delta G equals negative N times the Faraday constant times the voltage. And so now we just have to substitute in. When we did this equation, we saw that 2 electrons were canceled out. You know, the copper changing to copper was 2 electrons, the tin changing to the tin is 2 electrons. So that's what N is. So N is 2 moles of electrons. There's a negative sign. And the Faraday constant, that's a constant, so that's 96,500 coulombs per mole of electrons. And then there's the E0 value, which we just figured out was 0.48 volts. So if we substitute those all in, then we will get an answer of negative 93,000 joules per mole, or negative 93.5 kilojoules per mole of reaction. Okay, I'm kind of running out of space, but that's the idea. So you can tell that from the scoring guidelines. Okay, and that is this question. It's a lot of stuff.